imagine we have a probability distribution that's parametrized through an energy function like we've quickly discussed yesterday. Here. So in other words, P of x is parametrized to an energy function that has some parameters. And this z is a normalizing constant. It's the integral of e to the minus energy over the whole domain of x. And lots of graphical models fit, well, almost all of them fit this framework. But one thing you are interested in is, if we want to do maximum likelihood to train them, is the derivative of log p of x with respect to the parameters theta that come into the energy function. So it's simple. We take the log, and so when we differentiate, we're going to have just the derivative of the energy. And if we actually have a formula for this, that's easy to compute. And then there's the derivative of the log z, the log partition function. And that's the part that's going to give us trouble, even in RBMs, which are otherwise fairly simple. For RBMs, the energy we can compute exactly. We call it the free energy because notice that here there's no latent variable. X is what we observe. So we've sort of marginalized or eliminated the latent variables h I talked about. But anyways, let's look at this simple case. You can rewrite this derivative into this average of the derivative of the energies for all of the possible x's weighted by p of x, which is the model distribution. So if you, and the math is fairly simple. It uses a trick that comes up very often, which is that the derivative of p with respect to theta, you can rewrite as p times the derivative of log p with respect to theta. And the reason we want to do this is we're going to have some integral, and we want to be able to sample. So we want to have things like, some here and some here, and we're going to be able to approximate these kinds of things with the Monte Carlo. So that kind of thing here is an average over some distribution p of x of something we can compute. And we can use Monte Carlo, which means we're going to, instead of doing this intractable sum over all the configurations of x, we're going to use some sampling mechanism. So that's where the Monte Carlo Markov chain comes up, to get some samples of x according to p. And the average of the integrand here, the derivative of the energy, is going to be an estimator of that exact intractable sum, which could be an integral if x is continuous, for example. So in the case of the Boltzmann machine with latent variables, it's almost the same story. But now we may also need to run a Monte Carlo Markov chain over to sample h given x. But in any case, this was just to justify why yesterday I was talking about Monte Carlo Markov chains, because we need them to compute gradients of the log likelihood, which is sort of the ideal way that we would learn by maximum likelihood. Okay, now I'm gonna. Are there some questions about this, or? I mean, this equation is easier to understand. There's something that comes. I mean, one way to look at this is, one thing to notice is that the overall expression now has two kinds of terms. You see, it's always d energy d theta, but the sign is different. Here, there's a minus, because here we want to increase log p. That means we want to decrease the energy of the data, and we want to increase the energy of the samples from the model. And that's what I was explaining about pushing down on the energy for the examples from the data distribution, but pushing up for the examples that are dreamt by the model. So any questions about that part? Okay, so I'm going to skip to where I was yesterday, if I can remember. Right. So I was talking about how a denoising autoencoder can have a probabilistic interpretation by associating the autoencoder with a Markov chain in which we use our fixed corruption process, for example, adding Gaussian noise or whatever, and then we apply our learned denoising model, but think of it as a probabilistic model, a conditional distribution, and we sample from it, which you can think of as reconstruct and then add extra noise, which corresponds to the uncertainty in x, given x tilde. And do it again and again and again. And this Markov chain, we can show, estimates the data generating distribution in the sense that as our learned denoising model approaches the true denoising, the Markov chain that we get by running this denoising autoencoder approaches the data generating distribution. So we've generalized this in a paper that will come up in the next ICML to a situation where, in addition to having some kind of intermediate latent variable, we can have this latent variable actually have some free parameters of itself. So it's not just a corruption. And furthermore, instead of depending just on the previous x, it could depend on the previous h. So now we've created this Markov chain, which goes, sample h1 from, h2 from h1 and x1, h3 from, x2 from h2, and then h3 from x2 and h2, and so on. So basically, we update, according to this graph, these equations. So what we've added is we've added these connections. So now there's the state of the Markov chain is not just x, but the state of the Markov chain has x and a latent variable h. So it's an extension of the previous thing. And now we can think of any kind of complicated machine, basically, that has some state that is not just the visible variables and produces these pairs of x and h. And the x's are the things we care about at the end, but it can use these extra latent variables. And we can prove something similar about this setup. And we've experimented with it. First, so this is on MNIST, and these are sequences of samples from the model. So from the top is from a simple denoising autoencoder. From the bottom is using something that has a latent state. So now you see I can't cut this graph without including the h somehow. And if we look at deeper ones, I think I have deeper ones somewhere. No, I haven't. But anyways, we've trained deeper ones as well. I think I had a picture earlier, like this one. You're going to need both x's and h's as a state. And anyways, these seem to work better because they're deeper. And you can play games with them. So we've also trained them on faces. You can play games like you do with both machines. Like you can clamp some values and let the system sample from the others, which is essentially making them sample from the conditional distribution of those that are free given those that are clamped. You can do the same thing with Boltzmann machines. So in that experiment, we clamp the right-hand side of the image, and we let the chain fill stochastically the left-hand side. And here there's not a lot of ambiguity, so it's pretty sure what the left-hand side should look like. But for example, for this chain, we clamp the right-hand side of something that could be either an 8 or a 3. Both are a reasonable interpretation. And so it starts by filling it up as a 3, but then it switches to 8s, and it probably would come back to 3s eventually. So mixing between the possible explanations, which is exactly the kind of behavior we'd like to see. We've used this theory as well to explain two other algorithms. One is pretty old. It's called dependency networks. Dependency networks were proposed in 2000 in a paper by David Heckerman and collaborators. to make the learning of directed graphical models easier. So the idea is we're in the setup where there are no latent variables. You have observed random variables, and you have a graph of dependencies, which is, I guess, the kind of things that Ian explained this morning. And you'd like to capture the joint distribution of all these things. But you're going to parameterize that joint distribution through the conditionals of each variable given other variables. Now, actually here, it's not a directed graphical model. It's an undirected one. And so you're going to train a model that predicts each variable given all of its connected neighbors in the graph. And what's particular about what Heckerman proposed is that we're going to train a separate model for each of these conditionals, and they're going to have their own parameterization with their own parameters. And so that's very easy to do. You just train a neural net, for example, or whatever you want. That learns a conditional distribution of a single random variable. That's usually easy. For example, if it's discrete, you use maybe a neural net with softmax outputs. You could use any kind of parameterization if you want to choose whatever you prefer, so long as you can estimate conditional probabilities. And then they proposed a way to sample from this by just iterating over variables, resampling each variable one at a time. Well, it turns out that and actually this model was kind of not liked by many people because it wasn't clear what you were sampling from unless these conditionals were perfect, were somehow the right thing. Because those conditionals in general will not be consistent with each other in the sense that there would not exist a joint distribution whose conditionals would correspond to these. When you have a joint distribution, say you have two variables A and B, and you learn P of A given B and P of B given A separately with different parameterization that are not constrained to correspond to some unique joint P of A and B, then in general they won't be perfectly compatible in some sense. Not all the choices of these conditionals will be compatible. In general, they won't be, and that's the issue that people didn't like here. But it turns out that you can reinterpret what they've done by making a small change to the way you sample to make sure that the chain has a stationary distribution. So instead of going through the variables in order, if you go in a random order, then you can show this fits the theorems for the GSNs, the generative stochastic networks, and that there is a unique joint distribution that somehow corresponds to this, and it is the stationary distribution of this Markov chain. And furthermore, you can show that as you get better and better at estimating those conditionals, that unique joint, which is the stationary distribution of the Markov chain, gets better and better at modeling the data. So it has all the right properties we want as an estimator of the distribution. But it had been dismissed because there was not a good interpretation for it. There's something related to this, which comes out of work by my student Ian Goodfellow and our collaborators that was published at this last NIPS, where we train a particular kind of deep Boltzmann machine with what's called the mean field approximation, which I'm not going to explain now. But because of this approximation, once you've trained the Boltzmann machine, if you sample from it, you get things that are ugly. That doesn't look like it's a good generative model. So because we're not able to do maximum likelihood, people try other ways of training. And here, the training criterion for training was that we use a parameterization of the Boltzmann machine and some approximation to construct a conditional distribution of any subset of the inputs given the rests. So that means X minus subset. So we have a way to randomly pick some pixels and then predict those pixels given the other pixels. That corresponds to something that's, this kind of criterion is well known. It's a generalized pseudo-likelihood criterion. But here, because of the way this was constructed, there was no guarantee that, again, that it corresponds to a proper joint distribution. It probably explains why the samples were not nice. However, if you reinterpret what is going on as we're learning, basically, you can think of this as denoising this thing. You're saying, okay, I'm going to, the same as here, right? Basically, what are we doing here and here? We're hiding some of the variables by setting them to missing value. And then we're asking to reconstruct everything, knowing the right-hand side so we don't change them. And we only need to resample the missing ones. And that's exactly, here is a single one and here is, you know, some subset. And then again, you can construct a Markov chain which, you know, randomly resamples according to these conditionals. And this Markov chain you know, will converge to a distribution. And if you sample from this Markov chain, now you get nice things. So the original interpretation is, oh, we were approximating a deep Boltzmann machine gave rise to bad samples. But if you think about what you're doing as some kind of denoising, basically, and that defines a Markov chain which works, which gives rise to nice samples. All right. I want to mention, yeah, I'm going to skip this. I'm going to go to quickly about applications, and then I'm going to use the rest of the time to talk about practical matters when you want to train deep networks. So the kinds of tasks, first of all, on which these things have been used and for which they seem to be well suited, tend to fall in this category of AI tasks. So perception in general, they've been used a lot in vision, first for object recognition, but now they are being used for other tasks, object detection, segmentation. I'm fairly confident that, you know, within the next few years, we're going to see these techniques basically take over a lot of the vision tasks. There are many different vision tasks that were each approached with different techniques. Using so these techniques, I think, are going to make even more headway on these other tasks. Then speech, I've already mentioned. For now, it's been used mostly for speech recognition, but I predict that speech synthesis is going to be one of the next applications. Dealing with multiple modalities, not just, you know, images and sounds or images and text, but multiple modalities together. And of course, in the vision case, there's the temporal aspect as well. So video is becoming important. Video is challenging because of the computational burden, but, you know, our computational resources are increasing, continuing to increase, so it's going to become more and more feasible to apply these techniques to video. Natural language understanding and natural language processing in general, there's already a lot of work. I'll mention some of it later. And reinforcement learning and control is something that's starting. There was a pretty nice paper by the DeepMind people a few months ago, combining deep learning and reinforcement learning for learning to play video games. But of course, if you can learn to play video games just from images, you can learn to do all kinds of interesting things as well. In general, we expect these to work well when the distribution is complicated, in the sense that it has many variations, as I was talking about, but these variations are not random, they have some structure. So that this depth and all these priors we're putting are meaningful. And of course, you need lots of data. If you just have a few hundred examples, this is probably not going to be nice. On the other hand, you could have lots of data, maybe unlabeled, for some things, and maybe you can generalize on very little additional data for some related tasks. That's the transfer learning setup, and that works well. So the speech recognition thing I've already mentioned. The first work on this started in 2010, and by 2012, Microsoft and then quickly Google were using it in their products, and Microsoft was making an announcement about using them in their product. So I've shown this figure already. There are some numbers I got from Jeff Hinton on comparisons. This is already 2 years old. I'm sure the numbers have gotten better since then on various fairly large data sets that people at Google were comparing deep learning with traditional Gaussian mixture models with HMMs. Right. So there are other applications that are coming up. So there's a bunch of natural language application. In one of the first ones is language modeling, in other words, predicting the joint probability of sequences of words corresponding to, say, sentences. And that's used as a component in speech recognition and machine translation. Acoustic modeling is the stuff that maps the sounds to phonemes. That's what I was talking about just minutes ago. Tagging of sentences, either syntactically or semantically, means to answer questions about individual words. They're part of speech, to which chunk they belong, if they correspond to a particular named entity, like, you know, if we're talking about the president, in the context, maybe we are referring to President Obama, but that's the kind of thing that you have to use machine learning for. Semantic role labeling is another task where you're trying to figure out, you can think of it as a kind of semantic parse, so you're trying to figure out where's the verb and what is the subject, what kind of subject it is, what kind of objects, what words play which role with respect to the verb in the sentence. You can also use such models for a task such as sentiment analysis. So sentiment analysis is about predicting whether a short description is positive or negative. So usually these are comments on the web about products or events. And of course, companies want to know about that. Paraphrasing is a nice, interesting task involving the semantic aspect of language, where given a sentence, you'd like to produce another sentence that means the same thing. A simpler version of that is, given two sentences, you have to say yes or no whether they mean the same thing. So it may be a reformulation. And in a sense, this is very close to the machine translation problem, where you have two sentences that you'd like to know if they mean the same thing, but one is in one language and the other is in another language. So the tasks of paraphrasing and machine translation are kind of related nicely. And actually, one way to do these kinds of tasks, at least conceptually, is when you think about learning representations, is you've got a sentence here, and you've got a sentence here, and basically what you're trying to do is to encode them, say, in a fixed length vector, and then you want to know if they have the same meaning, then these two vectors should be close to each other. And if you actually want to paraphrase or to translate, then what you want to do is to couple this with a decoder that will output a sentence according to some distribution based on the representation you have in the middle. And that's a decoder, but it's a particular kind of decoder because its output is not of a fixed size. It's a variable length sequence. And in theory, you can do this with various models, like a recurrent net, which can handle multiple length inputs and outputs, or recursive nets that I was mentioning before. And this might be a generic way to do translation or paraphrasing. In the case of paraphrasing, the encoder and the decoder would match, correspond to the same language, but for translation, you would have, say, an encoder decoder pair for each language, but you would take, say, the encoder of French with a decoder of English to map French to English. So that's a very simple kind of schema that people are exploring. Now, besides sort of the traditional AI applications, there are lots of people looking at recommendation problems or advertising, fraud detection, personalization. All of these problems are kind of similar. So the reason why people look at this is because a lot of the business on the internet relies on these tasks. If you're selling things to people, then you'd like to know, what people like, so you can recommend them something. You can detect, behavior that's unusual, and you can, post ads that are relevant to the person's interest. So all of these are fairly similar, and you typically have users and products or things like that, and you'd like to predict some event like somebody clicking or putting up a rating, things like that. Then another kind of task where deep learning has turned out to be useful is doing some computation and some prediction on molecules. QSAR means quantitative structure activity relationship, and what it really means is, given a molecule, which you have to encode somehow as input to a machine learning system, you want to predict some property of that molecule. In particular, for pharmaceuticals, what they want to know is whether that molecule will bind to some other molecule, which is typically a protein that hangs off of some of your cells, and they want to know if this candidate drug will bind and have an effect on the cell. So whether basically two molecules will fit with each other, but they're going to try millions of candidate molecules for a single target. So basically, they're going to have a separate model for each target, typically. And it's been used also, and so there was some competition on Kaggle, one using deep learning by George Dahl from University of Toronto. And then there were people in Berlin that have applied deep learning for estimating properties of molecules that would otherwise require enormous calculation using approximations of the quantum interactions, but that can be approximated using neural nets. This shows this breakthrough that happened in 2012, just 2.5 years ago, with a paper that was presented at NIPS by Alex Krzyzewski, Ilya Sutskever, and Jeff Hinton, where on the task of finding the right class out of the top 5 from 1,000, they brought the error rate from 26% to 15%, which was a big improvement over previous years. And since then, as I said, there was another competition last year, and numbers have gone down even more. I don't know the exact numbers, but it's now less than half of what it was before deep learning was used. And it worked so well that it's now been incorporated in all kinds of products, including if you use Google Plus to organize your pictures. and you actually, search through your photos, and you use one of these 1,000 words that it knows, it works fairly well. So here are some examples that work. I've played with it, and it's surprisingly good. In my lab, we've participated last summer in a competition for recognition of emotional expression from images of faces, actually from short movie clips, so from Hollywood movies, and using a combination of deep nets for audio and video and image. We won this competition by an interesting margin, achieving 41% accuracy, whereas the next best were around 37 and 36%. All right, I'm going to skip this. I'm going to say a few words. I mentioned yesterday the neural language model. So this was one of the first attempts to use neural nets for modeling sequences of words. And it's been refined in many ways and improved since then. So in this NIPS 2000 paper, what we did is essentially just train a neural network that is trying to predict the next word given the previous words. So the output is 1 out of, say, 10,000. So it's a softmax with 10,000 outputs. And we'll see we can do things better now, but in those days that was simple to do. And it's just a neural net. The only difference is the first layer is a kind of convolution, meaning that the same weights are used for words at different position. So you can interpret what is going on as we take each word and using the same set of parameters, we encode it into a vector. So this is just a table lookup. But you can also think of it as each word has been encoded as a one-hot vector, so 0, 0, 0, 1, 0, 0, 0, with the 1 at the right place, depending on the identity of the word. Now, if you multiply a one-hot by a matrix, you get a vector, which is one row of the matrix, and that row is just the input to the next layers. So it's not very fancy in terms of neural nets, but the idea it was that it had some nice properties that were missing from traditional n-gram models, which are essentially non-parametric models in which you remember many triplets of words and their frequency of occurrence, and you mix those relative frequencies to estimate probabilities. What's happening here that's different is that we're learning a representation for each word, and I've shown you some examples of 2D projection of these representations. You learn a representation for each word, which in a sense you learn a set of attributes for each word. And because the neural net wants to learn a function that's going to be as smooth as possible, it's going to like to put the words that come in similar contexts near each other. And usually these are words that are semantically similar. So we've taken a problem that looks like a discrete problem. We just have symbols, and you'd like to estimate conditional or joint probabilities of symbols. And there's a cursive dimensionality problem because there are too many configurations of these symbols. We've mapped the problem of learning these joint discrete probabilities into working in a continuous space by learning these so-called embeddings of words. And in that continuous space, there's a kind of soft representation of meaning as these attributes that we can kind of visualize. What you buy with this is generalization. So if I've seen a sentence containing the word Japan, because Japan is close to China, it's likely that this will work with the word China as well. And that's because the neural net likes to construct a smooth function, remember I said, one of the basic priors of most machine learning systems is that they like, the prior is smoothness. So if I make a small change in input, I get a small change in output. That's what smoothness means. And if you were to think only in terms of symbols, well, the distance between Japan and China from a symbolic point of view is the same as between, cat and chair. This just, every word is different. But now we've mapped them to this space where if they have something in common, they'll be closer to each other. And that's how we get the kind of generalization that we've seen in recent years exploded a lot in many language models. And I've mentioned this thing already, that there's a kind of analogy property that seems to emerge from these representations. All right, so I haven't said a lot about applications, but I'm going to move now to practical considerations. If you have some questions about the applications, I'll be glad to try to answer. Yes?
So in speech recognition, for example, I was wondering whether the features that are learned by a deep learning algorithm have any physical interpretation or are in any way similar to conventionally used features in speech recognition, such as Mel-central coefficients or such.
Well, first of all, they often start from Mel-Kapstrom, right? I mean, there's been some people using lower level representation like spectral. That seems to work as well. And the features, they don't have a physical interpretation because it's not a physical model. But you could see their invariance. So if you play with these systems, you can display the features as you speak, for example, or as you vary, as you scan, for example, a part of a phoneme, say the beginning or the middle or the end of a phoneme, or if you play by changing the pitch or the or other properties, and you see many of these features being invariant to many of these things. So they've learned to be invariant because you're asking those features to be useful to predict something that should be invariant, which is the category. But yeah, it's hard to connect that to a physical model, like physical model of the mouth and stuff like that. All right. Okay, so as a reference for this part of my lectures, I encourage you to look at this paper chapter that's also a tech report on arXiv called Practical Recommendations for Gradient-Based Training of Deep Architectures. It contains a lot more detail than what I'll be able to talk about today. So what does it talk about? Okay, so it talks about the unsupervised pre-training trick, which I've already explained. But more interestingly, it talks about how to train these models besides the initialization. It talks about one of the main optimization technique that's been used and it's very popular and simple to implement, which is called stochastic gradient descent, which I will explain a bit more in the next slide. And how to set its control parameters, which are the learning rates. But it also talks about other hyperparameters. But the learning rate, so one of the messages you want to keep in mind is if you play with these things and you use some kind of gradient descent-based method, learning rate is the #1 hyperparameter that you have to be careful with. Almost everything else can be off, but your learning rate has to be set properly. If you're off by a factor or 2 or 3, it can be pretty bad. Either it converges too slow or it diverges, or it doesn't go down as much as it could. So I'll come back to that. I'll explain the idea of early stopping, the idea of mini batches. I'll hopefully, do I explain mini batches? No, I don't explain mini batches. So the idea of mini batches is that instead of looking at one example at a time, you look at, say, or 128 examples, or 64 examples. And the reason we do this is because modern computing hardware can parallelize and do computation much more efficiently if you can take do the same job 100 times in parallel rather than sequentially. So by looking at these mini batches of examples, you can be more efficient. If the mini batches are too large, then you lose some of the advantage of the sequential updating, and convergence becomes slower. So there's an optimal, but it only changes the rate at which you're going to converge, the speed, but it doesn't. It only has computational impact. You essentially would find the same kind of solution, whatever the mini batch size. Parameter initialization, we've mentioned unsupervised pre-training, but there are other approaches, and there's more research going on these days on this. The one hyperparameter that people think is important but turns out to be not so important is the size of the model, so number of hidden units. So, people think about neural net, oh, it's a problem, we don't know how to set the number of hidden units. It doesn't matter. Basically, you can pick it as large as you can afford in terms of computation time. And then you can use some regularization on top of that. It's not very sensitive to that. Of course, if your number of hidden units is too small, you're going to underfit in general. And it's hard to overfit. So yes, you can eventually overfit if it's too large, but it's hard to overfit. So and typically, it's more like your patience that determines how big of a network you are going to train. So in some sense, it's not a very sensitive hyperparameter. And it's determined by something that's very concrete and practical, which is how long you're going to wait, how good is your implementation in terms of computational efficiency and things like that. We use regularizers like L1 and L2. So L2 means minimize the sum of the squares of the parameters. And that's a very classical one. It's also called weight decay, and it's used, for example, in SVMs and logistic regression. It's a very, very standard regularization, and you can use it. The L1 regularization you can combine with the L2 regularization, and it's a bit different. It's the sum of the absolute value of the parameters plus some coefficient, which is a hyperparameter. And what it does is it tends to bring those parameters to zero. So you get some kind of sparsity. So if you use an L1 regularizer on the first layer, that will tend to eliminate some of the inputs that are useless, if there is such a thing. If you use it on the output layer, it will eliminate output features that are useless, if there is such a thing. But it might be, in general, a good thing everywhere to keep the networks slightly sparse, and that may help even optimization. The sparsity regularization that is mentioned here is different. It's not on the parameters, it's on the outputs of the units. And that's the thing that I've mentioned earlier with sparse coding and some of the related algorithms. You try to have representations that are sparse. Representations that are sparse are interesting because they're not rotation invariant, so it's like, there's axes of the representation corresponding to particular features have to have a particular meaning, because when they're off, they're off. You can't just take a linear combination of them and get the same level of sparsity. So the sparsity regularizer kind of sets axes in some particular way that's meaningful with respect to the distribution that you're trying to learn. Other things that are discussed in the paper is debugging. So how do you debug these things that are complicated, that are non-convex? So there are a number of tricks. Some of the tricks involve how do you make sure that your code computes gradients properly. So you can use things like finite difference approximations to verify that your derivatives are correct. You can also use various visualization tricks. You can verify that, if your code is good and you train on a very small data set, you should be able to overfit it. Otherwise, something's wrong, right? So if your optimization procedure is buggy, it wouldn't be able to train your neural net on a small data set. So these are examples of tricks that are discussed there. And then there is a really important question, which is deep learning methods in general have a lot of hyperparameters. So hyperparameters are the things that your optimization procedure doesn't learn, things like learning rates and number of hidden units and the coefficients for L1 or L2 and things like that. So how do we set these? So I'm going to talk about that a bit later. Now let's go through a few of these questions and a few others that are related, but that were not in this chapter. But stochastic gradient descent. So we've talked about gradients earlier yesterday. And gradients tell us about how a small change in some variable here, the parameters, give rise to a small change in the loss, and the ratio of these changes tells us how much we should change the parameters and in which direction. So this is the good old gradient descent, except that the reason we call it stochastic here is that instead of taking the loss on your whole training set, which is the thing you want to minimize, we're going to take the loss on a single example or on a mini batch, in the case of mini batch stochastic gradient descent, which is now kind of the standard, as I said, because of the kind of hardware we have. So it's called stochastic because you can think of this ZT as a random variable whose expected value, it's a random variable, it's one example sampled from the training distribution, one or 100 examples sampled from the training distribution. And the expected value of L of Z is the thing we care about, or the expected value of the gradient is the thing we care about. But we don't have that whole sum, that whole integral, which would be the correct gradient. We have a noisy version of it. You've got a stochastic version of the gradient. If we were to average over all the examples, then we would get the right gradient. But we don't want to do that because that would be very expensive. If you've got 1 million examples, or even 1 billion examples, which is some language modeling tasks, you don't want to wait for going through this billion examples to compute the gradient before you're going to change the parameters. Instead, you take a noisy gradient, which is wrong in particular, but is right in average, and make a noisy step. But the average of these noisy steps moves you in the right direction. So we're here, and say the right gradient is going in this direction. We go like this. But each of these steps costs us 1 million times less computation, so we can afford to do a lot of them. And the reason why this works is that whereas here the gradient was going here, maybe as you move in space, the right direction to go is fairly different. And so you can fairly quickly go in some weird path, which if you were to wait a long time by computing the exact gradient, you wouldn't be able to go very far anyways because this thing is turning. So there's no point in computing the exact gradient because it's not even, the gradient is not even the right direction to go. The right direction to go is something more complicated that has to do with second derivatives that we can't easily compute in general. And so there's no point in going exactly in the right direction. We might as well have a noisy version and we can compute much faster. So because of this really, really simple way of optimizing, at least for neural nets, works incredibly well. And of course, there's a lot of research to try to do better because you'd think with all the things we know about numerical optimization and second-order methods, we should be able to beat that very, very simple thing. But up to now, this remains kind of either competitive or better than other methods. There's a question in this, how do you set this epsilon t, this scalar, called a learning rate? So the simplest recipe is just to keep it fixed. If you don't want to waste too much time, you just keep it fixed, and now you have this one hyperparameter that you have to choose. And the simplest way of choosing it is try different values and pick the one which allows you to go down as fast as possible. So you don't need to do this for a very long time, but the way we actually do it in my lab, we use many machines in parallel, and we launch experiments with, say, 5 different learning rates. And when you get used to working with a particular type of architecture for a particular type of data set, you kind of know in what range the learning rates should be. If you find that, say, you've tried 5 different learning rates, and they should be spaced in a kind of exponential scale, right? So like 0.1, 0.01, 0.001, or something like that. If you find that the best one is on the border of your interval, that means you should try larger or smaller, because it means you haven't find the right interval that contains a good learning rate. Because you expect that the relationship between learning rate and the kind of accuracy you get after some time is a U-curve. Like many hyperparameters, typically, almost every hyperparameter, if you keep the other hyperparameters fixed and you look at whatever validation error, there is a curve like this. There's very simple optimum somewhere, and if you're too small, it's worse, and if it's too large, it's worse. In the case of the learning rate, the reason it's worse if it's too small is that your training is going to be slower, and you can look at the error curve. That helps also. So this is the number of iterations of training, and you look at the same thing, validation error, but now you can see what happens for different learning rates. They will converge at different rates, and of course you want to pick the ones that converges faster. It may be that if your learning rate is large, it will converge very fast initially, and then it won't be able to go down because it's arrived in a place where, think of it as a valley that's very sharp, and you can't really go down the valley unless you reduce your learning rate. So there are these other methods which are not that harder to implement, in which you add an extra hyperparameter which controls how fast you go down. So instead of having a fixed learning rate, you got a learning rate that varies as a function of t, typically as a 1/t type of relationship. And what this formula does basically is, so you've got 2 hyperparameters here, epsilon 0, the initial learning rate, and tau, which is a time scale. And the time scale, what it does here is, so this is t and this is epsilon t, the learning rate. It stays constant here until time tau, and then it goes down as, I guess, here. That's 2 tau. It's 1/2 of what it was after 2 tau, right? And then after 3 tau, it's 1/3, and so on. So it's going down fairly slowly, and there's some reasonable theoretical argument suggesting that a 1/t or something between 1/t and 1/t is the right sort of rate at which we should decrease the learning rate in order to get the best convergence. And then more sophisticated methods exist in which you actually try, this is a fixed schedule, fixed ahead of time with some hyperparameters that you set. But there are other ways of setting the learning rates which are adaptive. So there's, for example, the no more pesky learning rates paper. There's the AdaGrad paper, the AdaDelta paper, and personally, I think that this problem is not solved yet, but there is some research on it. And for some problems, some of these things work better than stochastic gradient descent. But there's a very robust and general purpose method. The normal SGD, possibly with this 1/t kind of decrease, is very, very robust. Questions about learning rates? Yeah?
Do you ever use momentum terms?
Yes. Momentum turns out to be sometimes useless and sometimes very useful. Momentum is a kind of cheap second-order method. So it's something like adding some inertia in the way that learning rates are, the way that updates are performed. So normally you would perform delta theta, like here would be epsilon times dc d theta. But instead of that, you could say, well, I'm gonna use a linear combination between this new direction that I want to go and the delta theta I had previously. And that's momentum. And there are variants of it, but that's the gist. And so if you imagine a kind of valley with imagine a valley. So it's kind of have a soft slope in one direction and a sharp curvature in the other direction. What stochastic gradient descent does is move around like this, and if we draw this with contour plots like this, these are contour plots of the costs. So stochastic, that's the valley here. Stochastic gradient descent would go like this. It would go down, but it would oscillate a lot between the sides of the valley. So what momentum does is, by averaging all of these little steps, you end up being able to make, so those that go in the direction of the mountains, the sharp curvature, cancel each other, and now you're able to go much faster. So that's a kind of cheap second-order method, which sometimes actually works quite well. Yes?
Is there anything like BFGS-like methods with stochastic gradients that estimate certain order?
So BFGS and conjugate gradients are typically batch methods. And that means batch means they have to wait to see a lot of examples before they can reliably take a step. So that's convenient for parallelization, but that means your steps you make your steps much more rarely, which means if your correct trajectory involves, a very complicated path, it's going to be very slow to converge. So one of the very simple techniques that seems to work well to combine these second-order methods, to use these second-order methods, is to start by stochastic gradient descent. Stochastic gradient descent very quickly finds a reasonable solution. So especially if your number of examples is very large, you don't even have to go through the end of the first epoch, the first pass through the data. You already have a reasonable configuration. And then after, say, one epoch, by stochastic gradient descent, you go and use a second-order method. And that works fairly well. It's probably one of the simplest and best ways to use these methods. Yeah, it's not yet established as the way that people will do it as a standard. Okay. Early stopping. Early stopping is one of these beautiful things from the 90s that every machine learning researcher should know about. It's a free lunch. There aren't that many free lunch around. I mean, this one is really worth it. So the thing with hyperparameters is that they're expensive because you have to try different values. And if you have many hyperparameters, this grows out of hand. So every time you can get rid of one hyperparameter for free, you should say yeah. Okay? So this one you can get rid of. It's the number of iterations for training. So if you think of the number of iterations for training as a hyperparameter, that means I would have to start a different learner, a different procedure for, I'm going to run 2 epochs, 5 epochs, 1,000 epochs, 200 epochs, I don't know. So I may have to launch 50 different neural nets. And of course, that's crazy because you can do it all with one run of the longest training. And that's what early stopping does for you. You just train for long enough, and you can use some heuristics to decide when to stop. And then you keep track of the best parameters that you found along the way. So as you train, say after each epoch or each sufficiently large number of updates, you measure your performance on a validation set, which could be small, so it doesn't cost you too much. You make sure you do this at a frequency such that there's not a big overhead by monitoring performance in this way. So let's say my validation set has 10,000 examples, then if I measure validation error every 50,000 example, then I have an overhead of less than 10%. It's not so bad. Because measuring performance is usually cheaper than actually doing updates anyways. So we monitor performance on a validation set, which is not the training set. So that's going to allow us to also set hyperparameters, not just like learning rate, which influence training performance, but those that involve regularization, like the coefficients for L1 and L2. And so we monitor performance, and we can display it. That's already useful. So we've got number of iterations. And we have validation error, or some validation loss, whatever it is, maybe some log likelihood, negative log likelihood. And so long as it goes down, we're happy. And if it starts to maybe oscillate or eventually flatten or go up, well, that means that some of the hyperparameter setting is such that we can kind of overfit, and we're starting to get into the overfitting regime here, or somewhere around here. So you can use some heuristic to decide that, okay, this, for example, the heuristic that we use in my lab is simply that if this is delta t, and this is delta t, and this is the best we found, and this is where we are, it's time to stop. We've found a minimum, and we've waited as much as it took to get to that minimum, and it hasn't improved, or it's gotten worse, and probably we've reached a minimum, and we can safely stop here. But keep that point as the model that we want to report at the end, on which we're going to compute test error. So this is a heuristic, and you can invent little variants of it, but the idea is really simple and works beautifully. And this way, you got rid of the hyperparameter number of training iterations. You still may want to have a maximum number of iterations because you want your jobs to be guaranteed to stop after some time, because you don't want to wait forever. But then it doesn't become such. It's not as important, and in particular, it can stop when when it's somehow converged sufficiently. All right. Long-term dependency. So that's not discussed in my chapter, but it's discussed in some other papers of mine, including ICML paper last year. And something I studied a long time ago, just after I finished my thesis. When you look at recurrent networks, so Remember, a recurrent network is a network that has that can model time and where you reuse the same computation. Actually, I have a picture. Right. So we've got an input sequence, and we've got a parameterized box that outputs a state and maybe outputs some predictions. And it has parameters. It takes the previous state and the current input, and it produces the current output and the current state, which feeds the next state, and so on and so on. And it's the same parameters used throughout. So you get this kind of graph of computation. And when you compute gradients, the gradients flow exactly backwards in the opposite direction, just as I explained yesterday. So you've got gradients with respect to the error coming from what if you make some prediction, then there will be a derivative of the error with respect to that state. Sometimes the error you get only at the end. But in any case, there will always be some gradients propagated backwards that correspond to the Jacobian of dxt plus 1 dxt for going from the step t to t plus 1. Okay. So what is it that goes wrong here? It's something very fundamental with the composition of functions, which is something we're at the heart of what we're doing with deep learning. If you compose many functions and they are nonlinear, then, well, actually, even in the linear case, you got funny things happening. If you compose many functions, then you get some kind of blowing up that can happen, or either going to 0 or going to infinity, or you can think of derivatives going to 0 or to infinity. And the way to see that happens is look at the derivative of, so we've got the composition here of states. So st influences st plus 1, which influences blah, blah, blah until st. And then st influences a loss, say. So now if we take the derivatives by the chain rule, we get dl dst is dl ds little t is dl ds big T. And then all the Jacobians, dst minus 1, blah, 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 up to the one we care about. So we multiply a bunch of numbers together, or matrices. In the case, these are matrices. But what happens when you multiply a bunch of numbers together? Well, they tend to either blow up or could go to 0. If the numbers tend to be less than 1, they go to 0. If they tend to be greater than 1, they go to infinity. And so your derivatives will basically be either very large or very small. So what kind of function has derivatives that are either very large or very small? It's a very nonlinear function, right? It's like 0, and then you've got some sharp decisions. Okay, so that's very nonlinear, right? The derivative is either 0 or in those regions it's huge. So that's the kind of function you get. In other words, you compose reasonably smooth functions, you get very nonlinear functions. Now, the fact that they're nonlinear is what gives them their power. That's what allows them to do really complicated things. But there's a price. The price is that those derivatives, which we use for training, become less easy to use because they become less informative. When it's close to 0, it's not very informative, obviously. And when it's infinite, it's dangerous to use it. It might blow in your face. And you're going to make a gradient step that goes too far. And then you've lost all the work you've been doing. So there's a dynamical systems way of thinking about this problem that's interesting, which is illustrated in this picture here. So what does the picture mean? It talks about a dynamical system. So you can think of this as a state that evolves. And you can think of, and so the state here says 2D in the picture. And the different paths with arrows correspond to a trajectory in that state, that space, right? So we start at one of the red points, say, and then the system evolves according to these updates, this recursion, and it may reach fixed points like A or B. That's what the picture is talking about. And the curve, the green curve, is a kind of separation between the starting points that will yield to A and the starting points that will bring you to B. So those regions on the right-hand side form what's called the basin of attraction of the attractor A, and those on the left-hand side form the basin of attraction for B. Notice that if you're right on the border, like these two red points, a very small change can make you go to one place or a completely different place. So what is the derivative there? It's huge, right? So a small change, the difference between those two red points, so that's like the delta x, gives a big delta x at the end of the sequence. You can end up at A or you can end up at B. Whereas if you take two other points that are in the middle, say, like you say this one and this one, they both yield to A. So now for a small delta x, you get no change in the final state, and so the derivative is 0. So that's the situation why we're getting these derivatives that are either large, rarely, or very small. So that's a setup of the problem. And it's also called the problem of exploding or vanishing gradients. And so it comes from the composition of many nonlinearities. So we've introduced a trick called the clipping trick. The first idea of this actually came from Tomasz Mikolov. And what it is basically is very simple. When the gradient is too large, you ignore it. You ignore its magnitude at least. So our version of it is if the norm of the gradient is above a threshold, then you reduce the norm to the value of that threshold. So if the gradient is too large that make you make a crazy step, you don't believe the magnitude. You have to realize that if there's a sharp derivative, it tells you in which direction to go. But if you take a step proportional to that, you'll go in a crazy place. So you don't trust large steps, because gradient descent only makes sense as an infinitesimal change. As soon as you make huge changes, it's totally meaningless. You can't rely on it. So that's the clipping trick that turned out to be really useful for training recurrent nets. But there are other tricks that are mentioned in this ICML paper, such as use of momentum I described earlier. It seems to be very, very useful for recurrent nets, such as appropriate initializations that avoid being close to a situation of exploding or vanishing. The use of architectures that give rise to sparse gradients that break a symmetry between what different neurons want to do. There's a problem with neural nets that they tend to have a difficult optimization arising out of the situation where all of the units want to do the same thing, or many units want to do the same thing. And these symmetries correspond to flat region of the cost, plateaus, that slow down training a lot. Leaky integration is something that helps to propagate long-term dependencies over longer sequences. There is a particular kind of architecture that was proposed in the late mid-90s called LSTM, which seems to help a lot with some problems. And there's a regularizer that we've proposed that tries to make these Jacobians, dxt, dxt minus 1, close to 1 somehow. And actually the initializations that we want to use also want to make this close to 1. So it's like we want this to be a rotation matrix. We want this to be of singular values close to 1. So trying putting all these things together, you can get pretty significant improvements in training recurrent nets.
Could you comment on how sensitive the final learned model is to the initialization of the weights and biases?
Very sensitive. So not to, because usually these are random initializations, right? So for a given sort of recipe for random initialization, it's very insensitive. In other words, let's say I choose a particular uniform distribution between, minus 0.5 and 0.5 or whatever. For every run, I'm going to get roughly the same thing. But if I change my minus 0.5 to minus 0.01, it's a huge change that could drastically alter the result. So initialization does matter, and not just the magnitude of the weights, but as we've seen in recent work, the sort of joint initialization. So like if they're initialized to be orthogonal, it seems to be better. And if we use autoencoder pre-training, for example, it seems to be better and things like that. So initialization does matter in the sense of this type of initialization that does matter. Specifics of which random seed you use doesn't matter very much. Yeah.
Would the difficulties you've been talking about with gradients and attraction,
Right.
would you expect in general to become worse as the network becomes deeper? Does that prevent us from going as deep as we would like?
Yes. Let me show you a curve about that. Obviously, there's lots of stuff I won't have time to go through, but so this curve answers your question. We are considering simple neural nets, in this case with a single hidden layer, but we've done it with more layers, where we train different networks of different sizes. And we try to see whether even the training error, forget about generalization, improves, and how much it improves as we consider bigger and bigger nets. So we would expect that as we train bigger nets, that the training error would get smaller after some big budget of time, after it seems to have flattened in terms of error. With this graph, but actually what happens is increasing the size doesn't improve as much as we would expect. So what this graph shows is on the horizontal axis, the number of hidden units of the network. On the y-axis is called the marginal utility, and what it is the number of training errors that you can knock off thanks to each extra hidden unit. So if I've added 100 hidden units and my marginal utility is 10, then that means I've gotten rid of 1,000 errors in this data set. Okay? And when the marginal utility is 1, which is the red curve, that means each hidden unit removes exactly 1 training error. And if it's below 1, it means each hidden unit does worse than removing 1 training error. And that's bad because we know we could easily get rid of 1 training error by adding a hidden unit that's specialized to that particular example. So if it goes below 1 and even approaches 1, that means we're doing something really bad with the optimization. So that means for larger nets, our current techniques, I don't think they work. And so we need to understand what's going on and fix it. All right. Okay, so one thing I want to, there's not much time. So one thing I'll go very quickly for a few things. I mentioned that sometimes you have a huge number of outputs through your neural net, like words in the vocabulary. So I mentioned 10,000, but actually more realistic models now have like 100,000 or even 1 million keywords, for example. And you don't want to have to do that much computation. It's going to be very slow. So there are certain tricks that have been used to reduce the computation to something manageable. One of the simplest tricks is to break down the, say, the vocabulary, which has, say, a million, let's say, say 1 million words. If you organize these 1 million words into 1,000 groups of 1,000 words, and you first predict which group the word belongs to, and then for each group, which word within it, then the whole thing becomes, the whole computation for training becomes proportional to 1,000 instead of proportional to 1 million. And you can make, you know, better, deeper trees and so on, but with this trick you can save a lot of computation. There are other tricks that have been proposed that rely on sampling methods that can be very appropriate in some settings. The other thing I want to make sure I don't forget is one of the really cool tricks to make to deal with hyperparameters that's discussed in my chapter, but also in this slightly older paper, is random sampling. So the traditional way in machine learning, and maybe that's how you've learned it, to deal with hyperparameters is you make a grid. Let's say you've got two hyperparameters. You organize a bunch of experiments where you try 5 different values of this one, 5 different values of this one. So you've got 25 experiments, and for each experiment you measure what your validation error is, and you pick the best out of 25. So that's what this shows. But it's a very inefficient method. If instead you throw darts to this square, you can get the same result much faster with less darts. And the reason this happens is that some hyperparameters will be have more influence than others. In particular, imagine one of the hyperparameters is useless. You're going to do a whole, for each column here, you're going to do all of the rows are going to be copies of it. And you're going to do all this extra work for nothing. So that's the very quick idea, but it's really worth it. It's much easier actually to program, because now if a run fails, it doesn't matter. You just keep throwing darts at the board, and this is so I encourage you to check this out. It's not just good for neural nets, but anytime you have lots of hyperparameters, this is useful. There's a lot of excitement now with methods that are more powerful than that, called sequential model-based optimization, where you're trying to optimize the hyperparameters on the fly, but I'm not going to go through this. All right, I'm going to leave you a little bit of time if you have some more questions. And for all the stuff that I missed, please, which is mostly challenges and questions, feel free to look at the slides online and write to me for questions.